Very good afternoon to all. So today's session, Geotechnical Engineering, the continuation of last week handled by Engineer Bilal sir from SRM Universities. Okay. Uh, so kindly convey the message to your classmates. Log into this GATE coaching class immediately because of already planned duration between 2 to 4. Okay. Don't be late. Okay. Forward the message to your friends already posted, but few students only join. Reminding your friends, you need to ask join this class immediately. Okay, don't waste externals time. Okay, sir will start the session exactly by 2:05. Okay, and similarly you can ask with external sir related to the questions, doubt, or reclasses. Okay, questions, everything you can directly ask with the external sir. Okay. Also, during the class hours, any network issue, voice and PPT is not visible, that kind of a problems also you can post in the chat box also. So we will check randomly chat box comments also. Okay, stay online.
Sir, shall I start the class, sir?
Sir, yes, sir. You can start, sir.
Okay, sir. Thank you, sir.
Okay, thank you.
So, good afternoon, everyone. Uh, Happy to meet you all again. So, we shall continue from where we left in the previous session. So, just a quick recap of what we have seen in the previous session. So, we were discussing the phase relationship. So we are discussing the phase relationship in soil mass. So phase relationship in the sense we all know that soil is a three-phase substance. Okay, so it doesn't fall in either a solid category or in a fluid category. It contains all three phases of matter. So hence we have seen some relationship between the different components in this mixture, in this soil mixture. So we have derived a few interrelationship between the base properties also. So the base properties in the sense which we directly derive from the phase diagram, and the interrelationship means the derivations or the formulas which are derived using two or more base properties. Okay, so that is called as interrelationships. So we have derived some interrelationships also. So the base properties which we were discussing was water content, a void ratio, a porosity, a degree of saturation, air content, percentage air voids. So all these fall under volumetric relationships category. And the rest we saw the weight relationships or mass relationship category. So in that we saw the unit weight, a bulk, dry, saturated, submerged, and finally the density of solids. Okay, so the first four represents the unit weights of a soil mass at different conditions. Okay, and the last one, this unit weight or density of solids, represents the in unit weight of the solid particle alone. Okay, so we are not considering the weight of the water and air present in this particular property, this density of solids property. Okay, so please be clear with the difference between these properties. Okay. Um,
Bilal sir, your voice is breaking, sir.
okay, sir. One sec. Sir, can you hear me now? Hello?
Yes, sir.
Yeah.
Yes, sir. Yes, sir. Students, all of you clear, sir voice?
Yes, sir.
Yeah, okay. Thank
Okay,
you.
sir. You can start, sir.
Okay, sir, sure, sir. If you have any difficulty in the voice clarity or anything, please stop the name there and intimate me. Okay, then only I can check. Okay, thank you. So let's proceed again. So one thing we have to be cautious about this unit weight is for any other material, say for example, we take concrete or steel or water or mercury, and these are the common materials we discuss. You may have come across during your previous semesters. Okay, so when we take fluid mechanics, you could have discussed the unit weights of water, oil, and mercury. Okay, so in fluid mechanics lab, we usually use mercury. That's why I included that here, even though it is not a construction material. And after that, you could have studied about the unit weights of concrete and cement in concrete technology, as well as reinforced cement concrete, DRC papers, design of reinforced cement concrete papers. And you could have studied about steel also, unit weight or density of steel in the same paper, DRC paper. Okay. Right. So the difference between the other construction materials and soil as a construction material is the other materials has a specific or an individual, or it has, we can say it only got one density or unit weight value. Okay. So the value of the density of a particular material doesn't change according to the circumstances or surroundings. Okay. But when it comes to water, I'm sorry, when it comes to soil, it changes according to the presence of or absence of moisture in it. Okay. So that's why in front of unit weight, we have some prefixes like bulk, dry, saturated, submerged, and all. Okay. For same soil mass, we can calculate all these 4 unit weights. Okay. So if we take a soil in its bulk condition, that means it got both water and air present in its void spaces. Okay. So that is called as a bulk condition. Okay. Even 99% water and 1% air means also it is a bulk condition only. Okay. So in that case, if you put the soil mass in a weighing balance and you measure its weight, and if you calculate the unit weight, what you are getting is the bulk unit weight of the soil. Okay, right. So if you take the same soil and put it in a hot air oven and you are keeping it for 24 hours at a temperature of more than 105 or 100 degrees Celsius, and you do the same process in the next day, what you are getting is the dry unit weight of the soil. Okay, for the same soil, once the water is removed from it, we are seeing a change in weight. Okay, so this is what I'm trying to tell here. Okay, so next, the same soil, the same after it is woven dry and after you have weighed it and you have calculated the dry unit weight, if you add water to the soil and you soak it completely, then you are measuring it. What you are getting is saturated unit weight. The 100% void space is occupied by water now. So if you are calculating the mass in this particular condition, what you are getting is saturated. And you are taking the soil mass container and putting it inside a water tank. Okay, submerging it. Then measuring it in the same position. Okay, using a spring balance or whatever, measuring it in the same position, then what you are getting is its submerged unit weight. Unlike other construction materials, this soil material only has this typical behavior. It changes or it behaves according to the presence of moisture in it. Okay, so all other construction materials, we can say it has a definite unit weight or definite density value. you can say in some extreme situations, even a concrete or steel can have a different density. Okay, the situation is if a construction or if a building uh, is to be constructed underwater, if a construction has to be made underwater, then there will be a change in its unit weight. Other than that, any other material doesn't have this dry unit weight condition or saturated unit weight condition and all the materials has, all other construction materials has only density or otherwise bulk density. Okay, so some in some underwater construction cases and all we can see the submerged density. Okay, other than that, no other material has this typical behavior as soil has. Okay, so this material, it behaves according to its moisture. So that's why we have crossed this 4 different unit weights: bulk, dry, saturated, and submerged. Okay, so for example, even if I have to say the particular value, if you can, if we are speaking of concrete, we can say the unit weight or the density of concrete as 25 kilonewton. Definitely we can say that. Okay, it will fall in 25 or some plus or minus a few changes will be there. But overall, on an average, we can say the concrete has a unit weight of 25. Okay, reinforcement concrete, we can say it. And the steel, we can say 7.85 specific gravity. It got a specific gravity 7.85. So we can say 78.5 kilonewtons. We can say it. Okay, unit weight of steel. But we cannot say a particular number for soil. Okay, because it changes from time to time according to the presence of moisture in it. Okay, let's move to the next topics. We have seen some important relationships, interrelationships between different properties, and we have seen some where we have utilized these properties also. Okay, now we can move on to the next problem. Okay, next different, we can see some other types of problems in this particular topic. So we have seen this particular problem in the previous class, and in that problem we have seen a soil in its wet condition and a dry condition, its weight has been given, and then the volume was given, and we have calculated these many properties in that particular sum. Now we can move on to the next sum. So this is a gate problem actually. Okay, so this is a problem asked in a gate some years back. So the question is, a contractor has compacted the base course for a new road and found that the mean value of the test samples show small w is equal to 14.6%. So what is small w here? So it is water content or moisture content. Don't expect the question, the property name will be given in the question. Okay, don't expect that. So sometimes it may be given with only the symbols of the property. Okay, so small w represents water content or moisture content, both are same. Okay, water content or moisture content here. So don't get confused, like so may it is w, so it may be representing weight and all. Don't, it's not like that. So small w represents water content here, 14.6%. The next property they have given is GS. It denotes what? Specific gravity. Okay, so specific gravity GS is equal to 2.81 and the gamma value. So gamma here denotes unit weight. Okay, so if nothing is given as a no prefix is given to the property name or no subscript is given in the symbol means it is denoting bulk unit weight. Okay, so if they have wanted to give a dry unit weight means they could have used gamma suffix d here. Okay, right, they haven't done that, so they have simply given gamma means it represents bulk unit weight in most of the cases. Okay, unless they are using the word dry somewhere in the question, the soil in its dry condition and all like that. If they have used that, then we can say it represents its gamma d. Okay, even that we have to make some judgment, then we can conclude that. Okay, so other than that, all other cases, if they are simply writing gamma means it denotes gamma b, that is bulk unit weight. Please keep that in mind. Next, the specifications require that, just a minute. So the specifications required that E value should be less than or equal to 0.8. So what is E here? Void ratio. Okay, so small letter E means void ratio. Okay, so the question is, has the contractor complied with the specifications? So the question is, has the contractor complied with the specifications? So that is the question. So just a minute. Yeah, okay. So the question is, has the contractor complied with the specifications? So here, the specification what they have given is the value of void ratio, it should be less than or equal to 0.8. So that is what required in this situation. So the contractor has to satisfy this particular condition. That is enough. Okay. So now we have to check what is the void ratio of this particular soil that has been used as a base course. Okay, so after compaction, they have given this properties of the soil, and we have to check whether the void ratio it is less than or less than 0.8 or not. Okay, right. The solution. So from unit weight formula, we have gamma is equal to GS gamma W into 1 plus W divided by 1 plus C. Okay, so using this formula, we can find the value of E here in this sum. Okay, so doing a small changes to the formula, we are rewriting it as 1 plus E is equal to GS into gamma W into 1 plus W divided by gamma. Okay, so here gamma W is unit weight of water and gamma represents the unit weight of the soil. Okay, so substituting the known values, we are getting, so G is given in the question itself 2.81, and the gamma W, it is unit weight of water. Okay, so by default we have to know it. Okay, they will not be given the value of unit giving that value here, unit weight of water. They will never give it that in the question paper. So we have to by heart it. Okay, so unit weight of water is 9.81. We all know that. So 9.81, we are substituting that, and then 1 plus W. So 1 plus W represents water content here. So it is given in percentage, but in during calculations, we have to use the decimal form of it. So 0.146 divided by gamma. It is unit weight of soil. So it is given as 18.2 in the question. So solving this, we are getting 1.74 in the right hand side. So taking that 1 to the right hand side, so we are getting the void ratio as 0.74. Okay, so which is less than the given value or given limit 0.8, and hence the contractor has complied with the specification. So this is the result. Okay, right. So hope you understand this. If you have any clarifications, you can ask. If you need any clarifications, you can ask. Or you have any doubt? Okay. So okay, then we can move to the next problem. So the next problem is a geotechnical laboratory reported these results of 5 samples taken from a single boring. Determine which are not correctly reported. Okay. So from a single boring means a single borehole is driven. Okay, so that means single boring. So from that single borehole, they have taken 5 samples. Okay, and have determined the properties of those sample in the lab. So what we have to do, what we are asked to do is determine which are not correctly reported. Okay, right. So for sample 1, so the water content value is 30%, gamma D. So here gamma D represents dry unit weight. Okay, so gamma D equal to 14.9 kilonewton per meter cube, and the gamma S is 27 kilonewton per meter cube. Okay, so gamma S here represents unit weight of solids, not soil. So gamma S represents unit weight of solids here. Okay, so please keep that in mind. Next, for sample 2, they have given some values and so on for up to sample 5. So we have to calculate, we have to check whether the data they have given for each sample is correct or not. Okay, so that is the task we are asked to do. Yeah. So how we are going to do is, the water content is in error if it is greater than the saturated moisture. Okay, so this is how we are going to deal this sum. We are going to check whether the water content reported it is less than or equal to the saturated water content. Okay, we have to check it. If it is satisfied, then we can say the readings reported are correct. Okay, so we can do that. So how we are going to calculate this saturated water content means, so using the formula SE is equal to WG. So using that formula, so again I'm just a small recap. So using this formula, SE equal to WG. During saturation condition, the value of S will become 1, and we can say the water content at that particular saturation condition as W sat. Saturated, water content at its saturation stage. So we can write like that, and this S will become 1 because 100% saturation. Okay, so we are going to check in this particular manner. So doing some small calculations. So from SE is equal to WG, we are converting S as 1 because under saturation condition, the value of S will become 1. So we are rewriting the formula into W is equal to E divided by G. Okay, so from this we are writing W is equal to E by G. So since saturation condition, we can write it as W sat. So that's what they have done here. So W sat is equal to E divided by G. Yes. We are substituting the corresponding values. So the value of void ratio is the original property, original formula of a void ratio is volume of voids divided by volume of solids. We are substituting that here. So you can see here. So VV divided by VS represents void ratio, and for GS, that is unit weight. I'm sorry, GS represents specific gravity. So we know the formula for specific gravity. What is that? Density of any material divided by density of standard material. So when it comes to soil mechanics, the specific gravity can be calculated using density of any material or density of soil divided by density of water. So gamma S divided by gamma W. So that is the formula. Since it is in denominator, we are writing in reciprocal direction. Okay, so GS is in denominator, so and hence gamma S is in denominator, and gamma W went to numerator. Okay, so that is how it is written. So from this, we are taking the unit weight of solids, we are again expanding it. So unit weight of solids, we know the formula, volume of solids divided by, weight of solids divided by volume of solids. So we are expanding gamma S as weight of solids divided by gamma volume of solids format. So we are getting this one here. Okay. So this one. So how we got this means, so from here. So we are writing gamma S as weight of solids by volume of solids. Since it is in denominator, so the volume of solids gone up. Okay, right. So after that, we are combining. We are cancelling this two, Vs and Vs here, and we are combining the remaining terms. So gamma W into Vv divided by Vs. Okay, right. So from this again, we are adding and subtracting volume of solids in the numerator. Okay, so the reason being, we have trying to bring the gamma d value here. The reason for doing this many tasks is we are trying to bring the dry unit weight in the formula. So that is why we are doing this derivation. The derivation. Okay. So from this, we are taking the volume of solids out, outside. I'm sorry. We are separating the volume of solids parameter. What we are getting is Vv plus Vs divided by Vs minus Vs divided by Ws. So here Vv by Vs, what it means is total volume. So this will become total volume. Volume of whites plus volume of solids represents what? Total volume. So and hence I'm writing that here. One second. So from this, what we done is Vv plus Vs divided by Ws. So we have splitted this term into this manner. So Vs divided by Ws. We are splitting this one into this. Okay. So from this Vv plus Vs, what this represents is total volume of the soil mass. So this represents total volume. So what we get is V divided by Ws minus Vs divided by Ws. So this total term is converted into this. Okay. So from this, we know unit weight, that is dry unit weight, is equal to weight of solids divided by total volume. So here we got total volume divided by weight of solids, which means we have to write like this: 1 divided by gamma d. In the similar fashion, we can write volume of solids by weight of solids as gamma s, because we know the formula of gamma s is, that is unit weight of solids, formula is weight of solids divided by volume of solids, and hence we are writing that in 1 divided by format, because it is in the inverse position. So we are writing that as gamma, like this, gamma s. So this is how we got this condition. So now we have derived the equation for water content at saturation condition. So this is the equation. So we haven't done the derivation of this particular equation before, but due to the requirement of this particular sum, we are in need of deriving a new relationship. Okay, right. That is the reason, because we don't have any other options left to find whether the given properties are correct or not. and hence we are doing these things, right? So now we are substituting the known values for every sample in this particular formula, and we are getting the answers for every sample like this. So for first sample, we are getting the answer as 30%. Okay, the water content given is also 30%, and hence the given values are correct. Okay, so from this we can conclude one more thing also. The given water content is also 30%, and the WSAT, that value of WSAT, it also 30%. What this represents means the first sample is already in its saturation condition. Okay, so the first sample is already in its saturation condition. Okay, so since W and WSAT both are same, both are 30%, and hence the given soil is in saturation condition. Right? So next one. So for the second sample, we are getting the value as saturation condition water content value as 18.5%. But the water content which was given in the question is 20%. Okay, so please keep that in mind. The water content of a soil sample will be maximum at its saturation condition. At its saturation condition only. So here, from the values given, we are calculating the water content at the saturation condition for a second sample is as 18.5%, but it has been reported as 20% in the data lab report. Okay, which means the sample 2, the results of sample 2 is not correct. Okay, they have made mistake in any of these three values. It could have been in reporting water content, in the calculation of water content, or it could have been the value of gamma D, or it could have been the value of gamma S. We don't know that. We are our scope is not to find where the mistake is. We have to just generally report whether the sample 2 is correct or not. That is what we are asked to do. So for second sample, the maximum value it can reach is 18.5% only, but it has been reported as for sample 2, the water content is 20%, which is much more than the maximum value which can be attained for the given data. So hence the second sample, the data they have recorded is wrong. Okay, so for third sample, we are doing the same process, and we are getting the value of saturated water content as 24%. So the water content given in the question is just 10% only. So the data reported are correct. One more thing we can get from this particular third sample is the soil still didn't attain its full saturation condition. It is still in its partial saturation condition only. Okay, means part of the soil is filled with this, a part of the voids present in the soil is filled with water, and the rest is filled with the air. So that is that one we can conclude from this particular third sample. So for first sample, what we said, since the water content and the saturated water content both are same, the soil already attained its saturation. For third sample, it is not the case. Okay, right. So let's go into the fourth sample. So we are getting the value of 22.1%. Okay, so we are getting the value of 22.1%, and the value they reported in the data in the report is, in the lab report, is 22% only. So here we have to make a judgment. So the value calculated is 22.1%, and the reported value is 22% only, which is slightly, very slightly less than what we have calculated here. So 0.1% only less. Okay, so we can take the result as a fair one. Okay, we can take the result as a fair one here in this particular condition, because the value, the difference is not very much like that happened in the second case. So here the value, the difference is just 0.1%, and then we can conclude the sample as a good one. So next, the fifth sample. For the fifth sample, we are getting the saturation water content as 18.5%, but the reported one is 22%. Okay, so and hence it is wrong. Okay, so this is how you have to deal with this kind of type of problems. Don't think that all the problems will be asked from the formulae that have been given in the book or that we have studied. Don't think like that. Especially in soil mechanics, in the exam sheet, you may be in a situation to create a new formula. Create a new formula means you are not researching anything there. So you are going to derive a new formula from the already derived formulas or derived relationships. You may be in need to do that. Okay, so don't expect that in first unit or in phase relationship chapter we are having 25 formulas. If I mug up this 25, I can answer any sum. Don't think like that. Okay, so in this particular sum, you have seen that we are deriving a very new term here, water content at its saturation state. Okay, sometimes you can get problems like this. Okay, so that is the level of, or that is the difficulty level of gate exams or UPSC exams for matter. Okay, right. Let's move on to the next one. The undisturbed soil at a borrow pit has a water content of 15%, void ratio of 0.6, and specific gravity of solids as 2.7. The soil from the borrow pit is to be used for the construction of an embankment with a finished volume of 40,000 cubic meters. The specifications for the embankment require a water content of 18% and a dry unit weight of 1.76 gram per cc. Calculate the quantity of soil required to be excavated from the borrow pit for the construction of the embankment. What would be its weight? What is the weight of the embankment soil? We have got so many questions in this particular sum. Okay, so many data is given, and we are asked to solve so many questions or properties here also, properties too. So let's write it one by one. Okay, so we are separating the given data as two portions. So first one is here we are dealing this particular sum in two different sites or two different locations. So the location one is the borrow pit location from where we are collecting the soil to build this particular embankment. Okay, so here location one is borrow pit, and location two is our site, our construction site, where we are going to construct this particular embankment. Maybe for any reason, for a highway project or railway, or maybe for a reservoir or whatever may be. Okay, so location number two is our site. So we are listing the properties of borrow pit in one area, one section, and we are listing the properties of our site, or the properties we need in our site in a second section. Okay, writing that in that manner. So dry unit weight of the embankment soil is 1.76 gram per cc. Here you may get a bit confused because the unit they have given is, it is in gram per cc format. Basically, for unit weight, the unit should be in newtons. Okay, kilonewton per meter cube. Okay, so gram per cc means it denotes they have given the density, not the unit weight. Okay, in words they could have they could have mentioned as unit weight, but you have to check the unit. Okay, check the unit of the value. Okay, so they have given G by cc means it is not exactly dry unit weight, it is dry density. That is what they have given. Okay, so but don't worry, it is not going to affect much here. Okay, so next, void ratio given at borrow pit, the void ratio is 0.6 and the specific gravity is 2.7. Okay, the next one, we are writing the location 2 properties in this next period. So volume of embankment, 40,000 meter cube of embankment has to be constructed, and then water content at the borrow pit is 15%. That is location 1 data actually. So water content at the borrow pit is 15%, and the water content at the embankment, what required is 18%. So actually in the borrow pit, the water content of the soil that we are going to use is only 15%, but during construction or after construction, the water content expected is 18%. Okay, so there's a slight property change here. So we have to compensate that here. Okay. Okay. So next, dry unit weight of embankment soil. We are calculating that. So we need to have a dry unit weight as 1.76 gram per cc. So converting that into tons per meter cube, we will get the same number. Okay, because for 1 kg it is 1000 grams. For 1 ton it is 1000. Yes. So for 1 kg it is 1000 grams, and for 1 ton it is 1000 kgs, and hence we can write grams as 1 into 1 gram, as 1 gram is equal to 1 into 10 power minus 6 tons. Similarly, in denominator we can write centimeter cube as for 1 meter it is 100 centimeter. Okay, so which means 1 centimeter equal to 1 into 10 power minus 2 meters. So since it is in cubical format here, so we can write 1 centimeter cube is equal to 1 into 10 power minus 6 meter cubes. So hope you are following me, or else let me write it here. What am I telling exactly? So 1.76 gram per centimeter cube. So this is what given in the question. Okay, so we are converting it into tons. The reason being the quantity of soil that is going to be excavated is much large, very large. Okay, so if we are calculating the entire problem in grams, by keeping the unit in grams itself, we have to deal with so many numerals. Okay, we are trying to reduce it, and hence we are taking a much bigger unit for mass here. So instead of grams, we are going for tons, not even kg. We are going for tons because the quantum of the project is that much big. So and hence we are doing that. So converting gram into tons. So 1.76 into 10 power minus 6. Hope you understand how we got this, because we know 1 gram is equal to 10 power minus 3 kg. Correct? Right only, right? Because we know 1 kg equal to 1000 grams. So we are writing that in reverse order. So 1 gram is equal to 10 power minus 3 kg. And we know 1 kg is equal to 10 power minus 3 tons, because in 1 ton we got 1000 kgs. 1 ton is equal to 1000 kilograms. So and hence 1 kilogram is equal to 10 power minus 3 tons. So 10 power minus 3 kg, already we got 1 10 power minus 3, and in conversion we are going to get one more 10 power minus 3. In total we are getting 10 power minus 6 tons. Okay, so for 1 gram this is the situation. So for 1.76 gram this is the situation. 1.76 into 10 power minus 6 tons. Similarly, in denominator, what we have is per centimeter cube is given in question. We know 1 centimeter is equal to 1 centimeter is equal to 10 power minus 2 meters. Why? Because 1 meter equal to 100 centimeter. We are writing that in reverse order. So we are getting 1 centimeter equal to 10 power minus 2 meters. Okay, or 1 by 100 meters. So 1 by 100 meter, I am going to take that in a numerator, I am writing it as 10 power minus 2 meters. So we are having centimeter cube here, which means 10 power minus 2 into 10 power minus 2 into 10 power minus 2. So that is equal to 10 power minus 6. 10 power minus 6 meter cube. So we have converted centimeter cube into meter cube. So cancelling 10 power minus 6 in numerator and the denominator, This gram per centimeter cube is directly converted into ton per meter cube. So this is a useful unit conversion, very useful unit conversion. What is that? And we are concluding that 1 gram per cc equal to 1 ton per 1 ton per meter cube. So this is one useful unit conversion you have learned today. If you haven't known that already, yes, some might have known that already. This will be useful in your field also. Okay, right. So we are doing that in the first step. So converting the unit weight of embankment soil into ton per meter cube format, what we got is 1.76 ton per meter cube. For 1 meter cube, from this, what we get is unit weight denotes means what? So unit weight means for 1 meter cube, how much is the weight? That is called as a unit weight. Simply weight means we are not relating that with the volume, but unit weight means for 1 unit of volume, how much? That is called as unit weight. So we have concluded that for 1 meter cube, this particular soil, it will weigh 1.76 tons. So for volume is equal to 1. So from this weight of solids, or weight of solids, we are getting as 1.76 tons, because we know gamma d. One second. So I'll write here. We know gamma d equal to weight of solids by total volume. So now we are substituting the total volume as 1. Okay, this is unit weight. Okay, so for when we substitute the volume of for 1 cubic meter of embedment soil, we are substituting the volume as 1. What we got is the weight of solid particles we require for 1 meter cube is 1.76 tons. You may wonder why we are doing this. The reason being, as we already said, the water content value differs for site and the borrow pit. Okay, so the only thing which is not going to change from the site and borrow pit is the weight of the solid particles. Okay, excluding the water and air component, only the weight of the solid particles alone will not change in both the conditions, in both the situations. Okay, and hence that is the reason why we are calculating the weight of solids in the first place. Okay, so for 1 meter cube, we require 1.76 tons. Okay, for 40,000 meter cube, we require 70,400 tons. Hope you understand how we got up to this step. I also said the reason why for calculating this weight of solids component. Okay, the reason being, this is the only component which will not change for site and borrow pit. So that is the only reason we are calculating this first. Okay, so next. So dry unit weight of the soil in the borrow pit is it is not directly given. Okay, we have to calculate that in the first place. So other properties of the borrow pit was given in the question. So other properties, what the properties that were given was the water content of the soil at the borrow pit was given. Okay, and then specific gravity of solids at the borrow pit was given, and void ratio here, you can note that here in the question. Water content, specific gravity, and void ratio of the soil at the borrow pit was given in the question. The unit weight of soil in the borrow pit was not directly given. So, and hence we are calculating that in the first place. So doing with the formula, we know gamma d is equal to G into gamma W divided by 1 plus E, and we are getting the unit weight of soil at the borrow pit as 1.6875 tons per meter cube. So at this particular moment, we can come to a conclusion that the soil required, the weight of the soil required at the site, it is 1.76, but the weight of soil which is available at the borrow pit is much less than that. So From this, we can conclude that we have to collect more soil and compact it. Then only we can achieve 1.76 tons in the embankment. Okay. Moving on to the next step. For weight of solids 70,400 tons, the volume of soil that has to be taken out from the borrow pit is, again, using the dry unit weight formula, gamma d is equal to Ws divided by V. From this formula, we are rewriting it as in the terms of volume. So taking volume to the left hand side and the gamma d to the right hand side denominator position, and we are calculating it as 41,718 meter cube. So again, please remember, the size of the embankment need to be constructed is only 40,000, but the soil that has to be procured from the borrow pit is 41,000. What is the reason? Because the unit weight of soil in the borrow pit is less, so that's why we are taking much more soil in order to compensate. Okay, that is why we are taking an additional 1,718 meter cubes volume of the soil from the borrow pit. Okay, so again, please keep that in mind. Weight of solids is the only term. It will not change. It will be same in both embankment and the borrow pit. Okay. So that is the reason we are calculating that in the first place. Okay. Now, the weight of the soil that has to be taken out from the borrow pit, which has a natural moisture content of 15%, will be, so we already calculated the volume here. So from this, we are calculating the weight now. So weight is equal to weight of solids into, that is total weight. Weight, capital W means bulk weight. Okay, so bulk weight is equal to weight of solids into 1 plus water content. Okay, so from this we get as 80,960 tons. Okay, so 80,960 tons of the soil need to be excavated or need to be procured from the borrow pit. Okay, so the weight of the soil in the embankment, which has a moisture content of 18%, will be more than that. The reason being, in borrow pit, the water content was only 15%, but in embankment, the water content is 18%, and hence the weight will obviously increase. Okay, so the reason, in the second situation, about 3% of the additional white space is going to be occupied by water. Okay, so that is the reason. So when we are replacing air with the water, the weight will obviously increase. Okay. Next, we are moving on to the next topic. If you have any doubts in the previous phase relationship topic, you can ask, or else we can move to the next topic. Okay, next topic, index properties of the soil. Okay, so if we calculate or if we find any value or any property of a material, there has to be a purpose for that. Why we need to do it? Why we need to calculate unit weight? Why we need to calculate void ratio? There has to be a purpose for that. Okay. Similarly, index properties of soil, and we are going to discuss a few properties of soil in the next few slides, and we are going to collectively call those properties as index properties. Okay, the name index, what is the reason for calling this bunch of properties as index properties means, so you can see in our record notebook or in a textbook, we have index in the beginning of the book. Okay, in our record book or in our textbook, we have index in the beginning. So what is the purpose of it? So index helps us to identify the content of the book. Okay, so index helps us to locate the content of the book or identify the content of the book, where it is. Okay, similarly here, this bunch of properties which we are going to discuss in the next few slides, this bunch of properties will be helpful for us to identify the type of soil, or in other words, this bunch of properties will be helpful for us to classify the soil according to some classification system. Okay, So why I'm using the word classification system means because there are n number of classification systems available for classifying soils. Okay, in India we are following Indian Standard Soil Classification System ISSCS. Okay, but in some other parts of the world they may be following USCS, means Unified Soil Classification System. Apart from that, there are some other classification systems as ASHTO soil classification system and all. Okay, right. So and hence uh, I used the term classification system. So for any classification system, okay, you have to, you may be in need of finding these particular properties that we are going to discuss now. So the tests carried out in order to classify a soil are named as classification test. The numerical results obtained on the basis of such tests are termed as index properties. Okay, so we can classify this index properties into two categories. So one is soil grain property, number two is soil aggregate property. The difference is, for soil grain properties, we will calculate the property of a single grain present in the soil mass. We won't calculate as a collective substance, collective mixture. We will just focus on a single grain present in a soil mass and try to find out some properties of a single grain. Okay, that set of properties we are going to batch it as soil grain properties. The second category of index properties are soil aggregate properties. Here we will calculate properties by handling the soil as a mixture. Okay, so as a collective mass, we will deal the soil and we will find out some properties, and we are terming it as soil aggregate properties. So some of the examples I have mentioned in the slide. The principal soil grain properties are the size and shape of the grain. So from one grain, you can do up to this only. We can calculate much any more properties from this particular grain. We can only calculate the size of a grain, and we can identify what is the shape of that grain. And in some cases, we can calculate the mineralogical character of the finer fractions. The mineralogical character of the finer fractions can be calculated using a single grain. So this will be useful especially in clay soils. Okay, so these are the soil grain properties. Okay, the soil aggregate properties, the most significant aggregate properties of soils, we can again categorize in two areas. One is for cohesionless soil, example sandy soil. Okay, so cohesionless soil, the prime example is sandy soil. It won't have any cohesion present in it. Okay, so it in other words, it don't have any self-binding nature. That is called as a cohesionless soil. Okay, you cannot take a chunk of sand in your hand and hold it. Okay, it will fall down. Okay, so it is called as a cohesionless property, a cohesionless soil. And the second category of soils are cohesive soils. Example is clay, or in other words, cohesive soils possess a self-binding property. Okay, right. So clay is a cohesive soil. Again, coming to our topic, the most significant aggregate property for cohesionless soils. Please keep that in mind when we are discussing about cohesionless soil. Uh, Please keep that in mind. We are discussing about sand. You remember like that, then only you can relate. Okay, what we are saying. Okay, I'm not saying only sand is cohesionless soil. There are some other types of soils also which fall under cohesionless soil category. But for instance, for your understanding, just try to keep sand in your mind when we are talking about cohesionless soil. Okay, so the most significant aggregate property for cohesionless soil is its relative density. So far, we have discussed bulk density, dry density, saturated density, submerged density, and all. And this is again one new term. relative density. So we will discuss what it is. And then for a cohesive soil, the most important aggregate property is its consistency. Okay. In the next slides, we are going to see all these properties. The first one, relative density, which is applicable only for cohesionless soil. So what it gives is the degree of denseness or looseness of a natural deposit of coarse grained soils. Okay, so this is what we will get from relative density, the degree of denseness or looseness of a natural deposit. Okay, so relative density is otherwise called as density index also. Okay, so this is another point. Next one, how we will calculate this relative density value means using this formula, ID is equal to E max minus E natural divided by E max minus E minimum. So here E represents void ratio only, no change in that, but the suffix or the subscript max, minimum, natural denotes for the same soil, we are going to calculate the void ratio in three situations, two extreme situations, one natural situation. So E nat represents the natural situation, and E max and E minimum represents the two extreme situations, meaning one situation is its maximum density situation. Okay, so that is the maximum density particular soil mass can attain, and we will calculate the void ratio in that particular condition. Then it has to be called as void ratio max, E max. And the second extreme situation is we will just spill out the soil grains and we will calculate its density. Then it is called as E minimum. Okay, in its loosest state, okay, density of soil in its loosest state, and we will calculate the void ratio from it, and we will get E minimum value. Okay, right. So this is the formula for calculating the relative density. So from this relative density results, we can classify the soil into these 5 categories. Okay, so if the value is less than 15, we can term it as very loose soil. If it is 15 to 35, we can term it as loose soil. If it is 35 to 65, we can term it as medium. 65 to 85 dense, and more than 100 we can call it as very dense. Sorry, actually not more than 100, 85 to 100 actually. Okay, not more than 100, it is 85 to 100. Okay, it, very dense. Next property for cohesive soil, the main aggregate property is consistency. So the consistency of clay soil can be calculated or can be measured using the Atterbull's limits. Okay, so consistency is a term which is used to describe the degree of firmness of a soil in a qualitative manner, not in a quantitative manner. So we are going to calculate the degree of firmness of a soil in its qualitative manner by using descriptions such as soft, medium, firm, stiff, hard, etc. Okay, right. So what this exactly or what this literally means is how with how much ease, okay, or in simply how easily we can deform a clay soil. Okay, we are given a block of a clay soil, how easily we can deform it, okay, change its shape. Okay, so using that, using these terms like soft, medium, and firm, we can indicate it qualitatively. Okay, so that is what we are going to do in consistency. And then the physical properties of clays are considerably influenced by the amount of water present in them. So depending upon the water content, 4 stages or 4 states of consistency can be used to describe the consistency. Okay, so 4 different water content states are liquid state, plastic state, semi-solid state, and the solid state. In between these 4 states, we got 3 boundaries. Okay, so from liquid to plastic, we have one boundary. From plastic to semi-solid, we have a second boundary. From the semi-solid to solid, we have the third boundary, and we are terming these 3 boundaries as consistency limits. Okay, consistency limits. And these three consistency limits are simple: liquid limit, plastic limit, and the shrinkage limit. When the soil transfers from liquid state to plastic state. Okay, liquid state means not it has it is like water. Don't think like that. So liquid state means when a soil attains a tendency to flow, then it is called as a liquid state. Okay, so from liquid state to plastic state, the small boundary is the particular water content in that boundary is called as liquid limit. From plastic state to semi-solid state, the particular boundary is plastic limit. From plastic limit to from semi-solid to solid state, the particular boundary is shrinkage limit. These are the three limits. Or simply, for your understanding, I can say, so take a soil. Okay, so take a soil and add water to it, make it to a flowable condition, make that mixture to a flowable condition. Okay, so we are adding water in percentages, and at a particular percentage, the soil mixture starts to flow, means that particular limit is called as a liquid limit. Okay, so now you are taking that mixture. Okay, we are taking that mixture and reducing the water uh, momentarily. Okay, at particular state, the flowable property got reduced and it start to behave like a paste, or that is called as a plastic state. Okay, right. So from that plastic state, again we are reducing the water content and we are getting a semi-solid state. Okay, so semi-solid state means, so in plastic state we have some uh, deforming property, but in semi-solid state we won't have the deforming property. So in semi-solid state, if we deal with the clay soil, it will start to break. That is called as a semi-solid state. So that boundary between these two is called as a plastic limit. And beyond that, if you continuously start reducing water, okay, and you are attaining that natural water condition, okay, then it is called as a semi-solid state. Okay, no more change in volume. Okay, so that is called as a semi-solid state, right? So these are the three consistency limits. So from these consistency limits, we are going to derive some more properties. The first one being plasticity index, which will be very useful for classifying the soil in Indian standard classification system. Plasticity index plays a major role, and we have to find that here. We should know how to find it. So plasticity index is the range of moisture content over which a soil exhibits plasticity. It behaves as a plastic. Okay, so that range. So that range is called as a plasticity index. Okay, so it is the numerical difference between liquid limit and plastic limit. So from this, we can calculate the plasticity index value. So IEP is equal to WL minus WP. So WL represents liquid limit and the WP represents plastic limit of that soil. Okay, right. So using this plasticity index, just like we did with relative density, we are going to classify the soil qualitatively like this. So if the plasticity index value is 0, we can call this soil as a non-plastic one. If it is less than 7, that is 0 to 7, it is low plastic soil. If it is 7 to 17, it is a medium plastic soil. If it is more than 17, it is highly plastic soil. So highly plastic soils are otherwise called as fat clays. Okay, so fat clays, and the clay soils with a very low plasticity index values are known as lean clays. Okay, fat clays and lean clays. Okay, so please keep this in mind. These are some other consistency related parameters. There is consistency index, liquidity index, and flow index. This won't have much usefulness in finding out or classifying the soil, so we need not go much deep into this. There again some more properties: toughness index, shrinkage ratio, So 1 point method for finding the liquid limit. Okay. The next one is sensitivity. Okay, again this is also a soil aggregate property. Okay, it is the ratio of the unconfined compressive strength of an undisturbed specimen of the soil to the unconfined compressive strength of a specimen of same soil after remolding at unaltered condition. So what this means, literally means, is if you take a clay in its natural state, okay, and measure its unconfined strength, we will get a value. Okay, now we are taking that same specimen and remolding it. Okay, we are mixing it, not adding any water to it, just remolding it. Okay, just we are doing some kneading action like that. Okay, just remolding it, and again we are doing UCC test, unconfined compression strength test. We will get a value lesser than the original one. Okay, due to the change in structural arrangement, we are getting this difference. Okay, right. So when we take a ratio of these both values in its undisturbed state and in its remolded state, okay, we will get the sensitivity. Okay, so based on the sensitivity, again we can classify a clay into 4 different groups. So if the sensitivity value is 1 to 4 means it is a normal clay, 4 to 8 means sensitive clay, 8 to 15 means extra sensitive clay, more than 15 means it is a quick clay. So please try to remember these values because you may get questions from this. Okay. Especially in 1 mark question in GATE exam, you may get questions from values like this. So what is the sensitivity value for a quick clay? If you get answer like this, and you will be presented with 4 different ranges, and you have to pick more than 15 from that. Okay, so please keep that in mind. So that is why I'm discussing these values here. Okay. The next property will be thixotrophy property. So thixotrophy is actually, it is a inverse of sensitivity, you can say that. Okay, so in sensitivity what happens, we are disturbing a natural deposit, okay, and hence its weight got reduced. Okay, that is what I'm sorry, its strength got reduced. So that is what happened in sensitivity. That is what we were studying in sensitivity. In thixotrophy, what it is it is a special property of clay, you can say that. Okay, so if the moisture of a disturbed clay strata, okay, so if the moisture of a disturbed clay strata is unaltered for a period of time, the clay soil will regain its strength. Okay, this particular property is known as thixotrophy. Okay, you are disturbing a clay strata and leaving it as it is, not adding any water or anything to that. After a period of time, if you go and measure the strength, it could have attained a part or some part of its original strength again. So that particular property is known as thixotrophy. It is a property of certain clays by virtue of which they regain, if left alone for a time, a part of their strength lost due to remolding. Okay, very important thing is the moisture content should not be changed. Okay. So this is attributed to the tendency of quasi soils to regain their chemical equilibrium. How this happens means they regain their chemical equilibrium by with the reorientation of water molecules, okay, in the adsorbed layers. Okay, so soils having more sensitivity are likely to attain larger thixotrophic hardening. Okay, if a soil, okay, if you are naming a soil as a highly sensitive one, it has the high ability to attain large thixotrophic hardening. Okay, so please keep that in mind. So activity is the slope of best fit line between plasticity index and the percentage of clay size fraction. Okay, so using activity you can classify as inactive, normal, and active clay. Okay, so less than 0.75 it is inactive, 0.75 to 1.25 normal, and more than 1.25 it is active clay. Next, soil classification. So what's the time? So 370. Okay, so in just 10 minutes I will give you an intro on soil classification, and we will discuss as per Indian standards, ISSCS or BAS classification system, we can call it as, because it is published by Bureau of Indian Standards. That is why we're terming it as BIS classification also. So ISSCS means Indian Standard Soil Classification System. You can study the entire guidelines in this particular code book, IS 1498-1970. They haven't changed it yet. So still 1970 version only running. Some reaffirmations are made, but not major changes. Okay. So IS 1498. So this is the code book number for this particular code book. Okay. So it is actually based on unified soil classification system. Okay. So just like our constitution, Indian constitution, which was derived from many constitutions all over the world. Okay. So this IS soil classification system is also, it is derived from unified soil classification system, we could say. Okay, we have made, in fact, we have kept the USCS as it is, and we have made only one change in it, and we just renamed it and said it is a full new one, but it's not the case actually. So we have made only one change to the USCS system, and we are calling it as a Indian soil classification system. Okay, that's not a problem. So what the change is, in a fine-grained soils, in US classification system, we have only two subdivisions, but Indian soil classification system, they have included one more in it. So in total, we got three sub-classifications or subdivisions in fine-grained soil category. So that is the only change between USCS and the Indian method. So nothing more than that. So okay, let's get into Indian classification system. And the major divisions are three categories. One is coarse-grained soils, and number two is fine-grained soils. Number three is highly organic soils. Okay, so in coarse-grained soils, majority of the soil grains will be in coarser size. Okay, so coarser size means more than 75 micron size. So major part of the soil mass, which we have taken for as a sample. Okay, so major part of the soil mass means more than 50%. Major part means more than 50% here. Okay, so more than 50% of the soil mass is contains coarser fraction. Okay, coarser fraction means more than 75 micron sized particles that are called as coarse particles. Okay, don't think as coarse aggregate in concrete technology. Don't take that here. So in soil mechanics, more than 75 microns means more than 75 micron itself, we will call it as a coarse soil. Okay, so please keep that in mind. Don't get confused. Okay, but in concrete, you could use the term coarse aggregate for gravel only, and the fine aggregate for sand. But that is not the case in soil mechanics. In soil mechanics, 75 micron is the boundary. More than 75 micron sized particles are termed as coarse soils, and less than 75 micron sized particles are termed as fine soils. Okay, so in fact, we will term sand as coarse soil in soil mechanics, but that is not the case in concrete technology. Okay, but please try to understand and don't get confused. Okay, sand falls under fine coarse grained soil. Okay, but in concrete, sand falls under fine aggregate category. Okay, please know the difference. Okay, coming to the topic. So coarse grained soils, in the soil, the majority of the fraction, that is more than 50% of the soil mass, will contain coarser fraction. Okay, in fine grained soil, the opposite of it. Okay, majority of the soil particles is in fine grained soil condition, finer particles. Okay, in third category, highly organic soils, Soil contains large percentage of fibrous organic matter such as peat and particles of decomposed vegetation and all. So this comes under highly organic soils. So before getting deep into this topic, let me give a small recap of how soil is formed. So not going in detail in that. So hope you already know it. You could have studied that in engineering geology subject. So in engineering geology, you could have studied the topic weathering of rocks. So from this weathering only, we are getting sediments, and the collection of sediments is called as a soil. Okay, right. So for the formation of soil, the base part is weathering. Okay, so I could say here the soil grains formed by means of physical weathering action, they will usually fall in coarse grained soil category. Okay, so please keep this in mind. Inorganic soils. Okay, the soil grains, the soil grains formed as a reason of physical weathering. It comes under coarse grained soils. Most of the time, this is the case. Okay, the soil which are formed by the process of chemical weathering, they come under fine grained soils category. Please keep that in mind. So highly organic soils, actually they are not formed by the action of weathering. So highly organic soils are usually formed by the decomposition of living matter. Okay, I'm sorry, decomposition of dead matter, dead organisms. Okay, dead animals or dead plants and all. Okay, so from the decomposition action, actually, this highly organic soils form in most of the cases. Okay, so this is the source of this categories of soils. Okay, let's move into that. Again, subdivision. So these are the primary divisions. Primary divisions means three major divisions, and again in every primary division we have subdivisions. So in coarse grained soils, we will again split that into two categories. One is gravel, another one is sand. I already told you in soil mechanics, even sand is considered as a coarse material. Okay, okay, so don't get confused when by comparing with the concrete technology. Concrete technology is a different area. There, sand is a fine aggregate, but here, sand is a coarse material, coarse soil. Okay, please keep that in mind. So, coarse grained soil, we are splitting that into two categories. One category is gravel, and another category is sand. So, for gravel, for a particular grain to fall under gravel category, its size has to be more than 4.75 mm. Okay, you are taking a single grain of soil and you are measuring it. If its size is more than 4.75 mm, then it is a gravel. If its size is less than 4.75 mm, then it is a sand. That's all. Okay, don't think it as a red soil, black soil, alluvial soil, colluvial soil, and all. We are just dealing with the size here. Okay, if it's more than 4.75, it is a gravel. If it is less than 4.75, then it is a sand. Next, the second primary division, fine grained soil, it is again subdivided into three categories. As I already said, in unified soil classification system, only two categories. Indian soil classification system, we made it into three categories, and we are naming it as low compressible, medium compressible, and high compressible. So in fine grained soils category, fine grained soils, we have two soils in it. Okay, one is clay and is silt. Depending on its compressibility, we are classifying those two into either highly compressible or medium compressible or low compressible. Okay, using its liquid limit value. Okay, if its liquid limit value is less than 35 means low. If it is 35 to 50 means medium. If it is more than 50 means 100. More than 50 means it is high. Okay, But in USCS method, unified soil method, we don't have these three. We only have low and high. Okay. If it is less than 50 low, more than 50 high, that is what the case in unified soil system. But in IS, this is the one. Okay. Right. So this is the reason we were discussing earlier in index properties, this liquid limit and the size and all. Okay. So again, these subdivisions further divided into groups, small groups. Okay. Coarse grained soil. Okay. So coarse grained soil as well as fine grained soil. Okay. I'm sorry, the coarse grained soil, that is sand as well as gravel. Okay. They are again grouped as clean and dirty. Okay. So clean and dirty, how we are terming this is the percentage of fine grained soil present in it. Okay. So using that, we will term either it is clean or it is not. Okay. If you, for example, if you take a mixture of sandy soil, okay, and it has if a mixture of sandy soil, and we can predominantly see only sand in it. Okay. And also we can see a major chunk of it as a clay soil, then the soil is not clean. Okay, we will discuss about the percentage in the later slides. So if it is the case, it is not clean. And if you are taking the mass of a sandy soil and it has only sand grains in it, and you can't see any visible matter in it, then you can call it as a clean soil. Okay. But actually not by visual examination we do it, by means of conducting some tests we actually do it, that we can discuss in the next slides. So again, the second subgroup will be well graded and poorly graded. Okay. So for this well graded and poorly graded category, we will go for the grain size distribution curve, and we will find the value of uniformity coefficient and curvature coefficient. Okay, so the CU and the CC value we find from the GSD curve, grain size distribution curve. So actually, grain size distribution curve is generated by means of conducting sieve analysis experiment. So when you conduct sieve analysis experiment, you draw the GSD curve. From the GSD curve, we can find out the values of CU and CC. By finding out CU and CC, we can term either a soil is well graded or poorly graded. Okay, so this is how the flow works. Okay. So before doing soil classification, it is important to do the sieve analysis. Then only you can find these parameters. And also, before doing soil classification, we have to do the consistency for some types of soils. Okay. So then only we can come to the soil classification and classify the fine-grained soils. Okay. Next. So they have given the range for well-graded and poorly graded. So for a sandy soil, the CU value, it should be more than 6 uniformity quotient, and the CC value, it should be between 1 and 3. Okay. For gravel, there is no change in CC, but in CU it has to be more than 4. Okay. Right. One important thing is, even if one of the condition is not satisfied, we cannot call the soil as well graded one. For example, a sand has a CU value of 7 and a CC value of 4. In this case, the first one, CU, it is satisfied, it is more than 6, because we have the value 7 in hand, and hence it is satisfied. But the second case, the CC value, it must be between 1 and 3, but the value we have in hand is 4, means one case only satisfied, and hence it is not a well graded soil, it is a poorly graded soil. This is how you have to term it, classify it. Okay. Right. So next, for fine grained soils, we will deal with the consistency values. Okay. So in that, we will be focusing on liquid limit and plasticity index. So for finding plasticity index, obviously we need to know the plastic limit also. Okay. Shrinkage limit will not have any impact or will not be useful for finding or for classifying a soil. Okay. So you don't need to worry about that. Even in field also, if you go to work, please keep that in mind. For classifying a soil, we need only liquid limit and plastic limit. We don't need shrinkage limit. Okay. Please keep that in mind. So using a Casagrande's chart, we will classify either the given soil is a clay or a silt. Okay, right. So next, some of the prefixes. I'm sorry, some of, not some of the. These are the prefixes and suffixes of ISSCS. So in Indian Standard Soil Classification System, we finally term a type of soil using two letters. Okay, in some special categories, in dual classification categories, we classify or we term a type of soil with four letters in pairs, in two letter pair format. Two letters separated by a hyphen. I'm sorry, two pairs separated with a hyphen. Okay. So this is the case. So in this, prefix means the first letter and the suffix is the second letter. So these are the possibilities for prefixes and suffixes. So in prefix, the letter G can come, S can be there, M, C, O, and PT. So PT is a special category. Okay, so for PT, there is no suffix. PT is the final answer. Okay, right. So PT is actually used for a class for naming the highly organic soils. So PT is useful there. Okay, so PT alone doesn't have any suffix. It is simply PT. That's all. Okay, so the possible prefix letters are G, S, M, C, and O. So the corresponding names being G gravel, S sand, M it is for silt, actually inorganic silt. M denotes inorganic silt, and C denotes clay, and O denotes organic silt. Okay. Similarly, the possible letters for suffix. For well graded, it is W, poorly graded P, silty M, clayey C, and based on the compressibility, we again have three more letters in terms of L, I, and H. So L represents low compressible, I represents medium compressible or intermediate compressible. Okay, wow. Next, H denotes highly compressible. Okay, so please keep that in mind. Don't get confused between M and I, because usually students do it. Okay, when they see the letter M, they think of medium compressibility. Okay, it is not the case. M stands for silt. Okay, and I stands for intermediate compressibility or medium compressibility. Both are same. Okay, intermediate between high and low. Okay, right. Next. So in this table, we can see the letters M and C. Okay, silt and clay. They have the chances to be in prefix as well as suffix. But apart from that, none of the other letters will be repeated in both the columns. You can see that. Okay, only M and C has the chances to be in both. It can be in prefix also in some conditions. In some other conditions, it will be in suffix. Okay, right. So we can stop right here. If you have any doubts, means please ask. If you have any doubts, means please ask. Okay, so in that case, we can close actually. I will send the material which we discussed to Professor, and he will share it with you. Okay, sir. Okay, then okay. Thank you. We can meet in next year, and only 3 days for the next year. Okay, thank you. We'll meet in the next session.